All right. So like I said, this guy's sizing fire pumps. For fire pumps, Kieran, we're going to be, when the mechanical engineers and the sprinkler guys decided that the water pressure in this building is not high enough to run your sprinkler system, what they do is they install a fire pump. So two things to know about the fire pump. If you guys look way at the bottom here, can you guys look at, I gave you two sheets. One of them has a transformer, the other one does not. So go to the one that says sizing fire pump feeder with no transformer here. Can you guys see that? So Adam, what I do at the bottom here, start from the bottom. I have what we call it the fire pump and the jockey pump. What they do is they have a big pump connected to the sprinkler system. Upon the existence of a fire in the building, that fire pump will pull the water and basically shower wherever the fire is located inside that building and extinguish that fire. Cool? That's the job of the fire pump. Karen, there's a little pump right next to it. It's called jockey pump. The job of that jockey pump, Adam, is to pressurize the system. It keeps the water pressurized, ready to go. Can I have thumbs up, Chad? We understand the jockey pump pressurizes the system. A tiny little baby keeps the pressure high enough so if you have a fire, the water will kick and the fire pump will take over to continue supplying the water to the sprinkler system. Cool? Jockey pump pressurizes the system, keep the pressure high enough in the piping system, the sprinkler system, and the fire pump, upon the existence of a fire, will supply the sprinkler system with the needed pressurized water. You need pressure now. Okay, so that's what we have. So let's start at the bottom. You have a jockey pump. Typically what they do is they have a jockey pump and a fire pump. You need a branch circuit. I'm sizing them. Can you guys see these numbers are related to the bottom table that you have? So I have 1 and 2. These are the branch circuit for the fire pump and the branch circuit for the jockey pump. Then we have a controller, 3 and 4. Can you guys see that? Everybody can see that? So starting from the bottom, I have 1, 2. 1 is the fire pump branch circuit conductors. 2 is the jockey pump branch circuit conductors. And 3 is the fire pump controller. 4 is the fire pump, the jockey pump controller. And Adam, right next to here is where you find the code references to them. And the last column is how do you calculate these? So on the test, you grab that piece of paper in front of you, Derek, and you apply it. So for example, can you just see that? To calculate the branch circuit for the 2 pumps, you take the full load current from the NDC code book. Can you just see that? Multiply by 1.25. Cool? Can you have thumbs up, Chad? Cool. Next, to size the controller, fire pump controller, for both of them, you take the horsepower voltage and go to find an NEMA. Exactly what we did, guys. No difference. Same thing for the jockey pump. You take the horsepower and the voltage, and from DeWalt book, you can go find an NEMA. What I did, guys, I gave you this sheet, and then I have an example I'm going to go over. Everybody understand? You got this sheet, and then we're going to go over an example. Okay, but you need to understand this sheet, though. So up to 1 through 4, Adam, is okay? Does it make sense? 1 through 4, Derek? Karen? 1 through 4? Okay, let's go to 5. 5, can you guys see 5? 5 is the feeder that's coming to the controller that feeds both of them. Okay, 5, controller feeder conductor. Where do you find the references, guys, about it? I gave you the NEC code book for 430.250, 695.6b. Cables will be from 310.15b16 at 75-degree column. So Adam, when you size the feeder for the 2 of them, here's what you need to do. The controller feeder, you take 1.25 times both full load current. Did you guys see that? You multiply by both full load current. You add them up, and you size your conductor. Any comments, guys? Any questions about number 5? Questions about number 5? Derek, number 6. Number 6 says auto transfer switch, right? Can you see them? For auto transfer switch, it says when we size it, we go to DeWalt 3-12, we go up if it's not standard. And how do you calculate it? Based on the amps, and you take 1.25 times the sum of the fire pump full load current and the jockey pump. Does it make sense, guys? So that's what you're going to have when we have a final and when we have the test on Monday, next Monday. You have this sheet in front of you. When I give you an example, you're going to apply it because there's a lot of rules and regulations. Okay? There's my friend, Matt. That's all right. Okay, so that's your number 6. Any question, guys, up to number 6? Can you guys see how they're sequential? Up to number 6. Let's go to number 7. Number 7 is when you have a fire pump, Derek, you have to have 2 sources of power for the most part, right? One source Adam is coming from the electrical utility, and another source, Karen, is coming from the generator. Electrical utility generator. Can you guys see that? On the electrical utility side, we typically, you have to feed it from, can you guys see that? You feed it from the line side of the overclock protection device. Can you see where the feeder, not here, not from the panel, from the line side. Okay, so Adam, when you feed it, can you guys see where, here's the circuit breaker, you feed it from this side, not here. So from the line side. So that would be like two mains. One main is going to the fire pump and one main going to the whole building. Can you guys see that? Then it comes to a circuit breaker, of course, and then it goes to the auto transfer switch. Then you have a generator, Adam. From the gen, you have a circuit breaker, and then you go to the auto transfer switch. Okay, so everybody understand how are we feeding these fire pump system? Matt, I gave you 3 sheets. Grab the sheet that does not have a transformer in the middle here. And what we're doing is we're sizing a system for a fire pump. Here is my jockey pump that pressurizes the system. Fire pump is the one that pushes the water, pressurized water into the sprinkler system up on the existing fire. So we size 1 and 2. Can you see that 1 and 2 here? These are branch circuit. 3 and 4 is controllers. Here's 1 and 2, 3 and 4. This is where the code reference is here. And this is how you calculate them. Okay? So I'm right now at number 7. Okay, look at number 7, guys. Number 7 and number 8 are the feeders coming, one from the utility and one from the generator. Okay, let's go to 7. 7, conductor from the main service, conductor from the backup generator. How do you size them? Same thing, Adam. 1.25 times the sum of these 2 pumps. Everybody can see that? 1.25 times the sum of the 2 pumps. Very, very clear. Then we go to 9 and 10. The last thing is 9 is the circuit breaker from the utility side. 10 is the circuit breaker from the generator side, because you have 2 sources. So you go to 9. 9 overclock protection device from the main service size. How do you size it? Here's all your references in the NDC code book from Article 695 that talks about fire pumps and other articles. LRC, we size the circuit breaker from the utility size, guys, based on the locked rotor current. LRC is locked rotor current. You take M as multiplier, you're going to see from NDC code book, which is from table 430.7b, multiplied by the horsepower, multiplied by 1,000, divided by the voltage and 1.73. And then you add the 2 locked rotor currents for the 2 system. You add the 2 locked rotor currents for the 2 of them. This is from table 4, right here, Derek. 430, yep, for each one of them. You're going to see we have an example coming in a second. In the overclock protection device from the generator side, you take 2.5, guys, and multiply it by the full load current of the fire pump. Then you take the overclock protection device of the fire pump and you add it to the full load current of the jockey pump, and you size your overclock protection device down. Can I have thumbs up, Chad? We have, this is what I'm going to be going over in an example. Everybody's okay? Karen, does it make sense? So that's what's going to be on your test, guys, on Monday, basically. Cool? I do have another sheet. I'm going to wait for the other sheet until I do the example, guys. Let me go over this sheet and then the second sheet. The only difference between the second sheet, Adam, is there's a transformer here. Okay, can you guys keep this in your hand? And let's go do an example about this, shall we? Everybody's good with that? All right, so grab this one, keep it handy. Let's go and do an example. All right, so here's the example that I have. Okay, so Karen, I do have a 50 horsepower motor running at 480 and a 5 horsepower jockey pump running at 480, and the code letter for the fire pump is M, the code letter for the jockey pump is N. Did you guys hear me? That's all what you need to apply these 10 things. So the question would be, Derek, is let's go calculate these 10 things for these 2 pumps. Can I have thumbs up, Chad? We fully understand what we're going to do. So grab that sheet, guys, that sheet, and we're going to go apply it. Everybody's good with that? 50? You guys have the sheet. There. I did give you this sheet. Right? Matt, you have that sheet in front of you. Okay. All right, so everybody knows what we have. We're going to go apply it. Okay, the first thing that you need to do, gentlemen and ladies, is you need to go find example, like I said, 50 horsepower at 480, jockey pump at 5 horsepower at 480, fire pump branch circuit. The first thing you need to calculate, and I have that one, guys, fire pump branch circuit for you, the fire pump branch circuit. So Adam, you go to 430.250 under 480 voltage, and when you go there, gentlemen, you're going to find it's 65 amps. 65 amps. So you're going to go to this table and find the full load current. You guys have done that before. It's nothing new. You're going to find the full load current for the 50 horsepower from the NDC code book. You do have this one in front of you guys, so expedite the process. Then, gentlemen, then you multiply it 65 by 120, and that will get you 81 amps. And then you take your 81 amps out, you take it to 310/15B16 under 75-degree column, and that will get you a healthy three conductors number 4 RHW, an installation I use with the fire pump. RHW, not THH, an RHW. More robust for the fire pump. Any comments, guys? Any questions? Any comments? Any questions? Does that make sense, everybody? See how that is easy? On the test, there is no reason not to ace it. You guys have that sheet in front of you? Okay, shall we go to the jockey pump? This is number 1. And we're following a sheet like this, guys. You see that sheet in front of you, right? Okay, Adam, good? All right, so let's go to the second one. Second one, jockey pump, 5 horsepower motor. Gentlemen, we're going to go to the 5 horsepower motor, 430.250. You're going to have 7.6 amp. And then the same thing, 7.6 amp multiplied by 1.25, get you a beautiful 10 amps. And you take the 10 amps, and that will get you 3 conductors. 3 conductors, number 12AWG RHW.
Is 12 the smallest they're supposed to go?
You're absolutely right. So can I use 14? Yes. But you don't want to, in a commercial industrial building, guys, don't even mention 14. Cool? You're absolutely right. The minimum, I could have gone with 14, right? You guys found 14. So you don't want to use this 10, 12. Does it make sense? 12 is your minimum in commercial industrial. Okay, next. The next thing we need to find, Karen, is the controller. You guys, for controllers, can you guys grab DeWalt? You go to 6-4, grab DeWalt, go to 6-4, based on the horsepower and 480 and the voltage, the horsepower and the voltage. This will get you a healthy NEMA number, NEMA number 3. NEMA number 3, that's your contactor, directly from DeWalt, 6-3. Make sure you know how to use it. 3-phase controllers based on the voltage. Okay, the jockey pump controller, the same thing, Adam, based on 5 horsepower and 480. The jockey controller should be NEMA 0. NEMA number 0. Both of them, Matt, both of them shall not have an overload. Guys, fire pumps is required not to have an overload like other motors. The reason, because if you have a fire in your building and your fire pump is running, do you care about overloading the fire pump when half of your building is on fire? Is that a concern to you? So what they do is the code require you are required not to have an overload protection net. Meaning if it gets overloaded and get on fire because of overload, let it be. You're already on fire. So you're just holding the ground until the firefighters come. So you're gonna let it keep kicking that water where the fire is located. Does that make sense? No overload in it. Any question, guys, about sizing the controller? DeWalt 6-4. And Matt, all this information is right in that little sheet that you guys have. So on the test, you grab that sheet, you follow step by step. That's why I'm not. Okay, let's go next. Am I going too fast? Too slow? Good? Okay. Let's go to number 5. So we're going step by step. Controller feeder. Number 5, now remember, we're following step by step. Matt, does it make sense with the sheet that you guys have? Right? Okay, so we're not jumping around. If you guys look at the sheet, it will tell you, right? What do you do? Derek, can you remind me what we do? We take 1.25 multiplied by both full load current, right? There you go, 7.6. You add them up and then you multiply. They'll give you 91 amps. and then you take your 91 amps, atom, 310 and 15B16 75-degree column. That will get you a healthy 3 conductors, number 3 RHW. RHW. Does that make sense? Does it make sense, guys? Does it make sense? That's your conductor. ATS. To size the ATS, if you guys look at that's number 6, the same calculation we do. We use 1.25 times same calculation that we did above. 65 plus 3 point, oops, not 3, plus 7.6. Add them up, get you 91 amps. And then you get your 91 amps, take it to DeWalt, 3-12, that will get you 100 amp. 100 amp circuit breaker. 100 amp circuit breaker. 100 amp circuit breaker. Auto transfer switch. Yes, sir. Yes, sir. We're going on the disconnects. ATS, go to disconnects. That's as best as you can do it. You know, that's kind of a guide for at least for the calculation. Derek, do you see that sequential, straightforward, now no gimmicks, step by step? Really not a whole lot to it. Okay, so that's number 6. Number 7, conductor from service, same as number 5. Can you guess that? No, the conductor from the service, it says same as number 5. So 3 conductor, you go to step number 5, same, 3 number 3 RHW, done. Conductor from the generator, same as number 5. So that will be the same conductor. 3 number 3 RHW. Same conductor. Can you guys see that? No gimmicks, nothing at all. Nothing at all. Matt, makes sense? That snow is getting you quiet again. What's going on? Okay, number 9. Now, number 9 is the overcome protection device. If you guys look at it, number 9 from the service. The overcome protection device from the service, it's kind of a funny bit, boy. You need to go find, can you guys see what the sheet says? It says you have to find the multiplier, multiply by the horsepower, 1,000, divided by the voltage in 1.73. This is fire pump, the fire pump horsepower. We're going to do it for both. Okay, so here we go. So if you guys, what's the multiplier? What was the multiplier for the fire pump? The code letter M. From code letter M and table 430.7b for M, you're going to find the upper limit is 11.19. Multiply it. Derek, what's the horsepower of that boy? 50, thank you. Multiply by 1,000 because it's given in 1,000. Divided by 1.73. Derek or somebody, what's the voltage of this system? 480, thank you. So multiplied by 480, and that will get you a healthy 674. 674 amp. So that's my amp. 670.
Do that at the locker return for me to want to.
You got it. Now this is the fire pump. Right underneath it is the jockey pump. We need to do the same thing for the jockey pump. Jockey pump. So the jockey pump, guys, is what's the code letter for the jockey pump? The code letter is what? N. Based on N, it's a 12.49 multiplied. What's the horsepower, Matt? 5? Yep, thank you. 5 times 1,000 divided by 110. Oops. Divided by the whole 1.73 times 480. And that will get you a healthy 75 amp. Does that make sense? So you find the full load current for both these boys. Does that make sense? Okay. Find the full load current for both of them. Then, second step is add them up. 674. You need to add them up. Plus 75. That will give me 749 amps. Add them up. Find the full load current, add them up. Then take the 749 amp, take it to 240.6. If it's not a standard atom, you're going to go what? We're going up. And the sheet will tell you. This is an 800 amp circuit breaker. So from the that's the difference between a fire pump and any other motor. There, on a fire pump, they size the overcaptation device based on the locked rotor current. Unlike other pumps, where they size it based on the full load current times 2.5, from the service side, they size it based on the locked rotor current. Meaning, guys, because it's so important, they want that fire pump to keep working until it burns itself in the process of protecting your building from the fire, which makes sense, right? They want the fire pump to hold the ground until the firefighters pull in and take care of business, basically, and support the firefighters in fighting that fire. Does that make sense? So, do we care about installing the fire pump? Do you care if the locked rotor current will guarantee you guys when you oversize it? Meaning, even if the fire pump stalls, the circuit breaker would not trip. We wanted to make sure it keeps kicking. If it stalls and burns itself, big deal. We already have fire in the building. Okay? So that's different. That's different. That's from where, Derek? This is from the utility side. Now let's go do it from the generator side. See how it's slightly different from the generator side. Okay, generator side. From the generator side, that's number 10. Generator side, guys, different. Look at that. You take 2.5. This is from an EC code book for motors, which is, what was it? From table 430.52. This 2.5 is from table 430.52. And you multiply it by the fire pump 65, and that will get you a healthy, when you do that, 162.5 amps. Okay? That's step number 1. Then you take the 162.5 amps, take it to 240.6, go up if it's not a standard, and that will give you a healthy 175 amp circuit breaker. Okay? This is, we're not done yet. Listen, we're not done yet. So that's what you're going to get. Then, overcurrent protection device, guys, from the generator, the way you need to do it, then you take the 175 amp that we just add to it. If you look at 7.6 amp, what's the 7.6 amp? That's the jockey pump amps. Add it to it, that will get you 183 amps. And then take the 183 amps, 240.6, go down, will ya? If it's not a standard, 240.6, take this one to 240.6. If it's not a standard, you go down. Okay, what's the next standard down? 175 anyway. So we went back to 175. We went back to 175. Cool? So from the generator side, Derek, the circuit breaker is 175. From the utility side, the circuit breaker is what? It's 800. And the idea, guys, is what's the likelihood? Take this. What is the likelihood that you have a fire in your building and at the same time you lost the service to the building? Could it happen? Could happen. You know? And at the same time, your fire pump stalled. Look at that. You have a fire in your building. You lost the power to your building, the electrical power, and at the same time, your fire pump stalled. So these are highly unlikely. So they allow you on the utility side to oversize the circuit breaker. On the generator side, it does. If you lose power and you're running on the generator, this circuit breaker will allow you to run, right? Now, if your pump stalls, then it might trip. But it's like taking a lot of chances, so it's highly unlikely. Could it happen? Yes, but it's highly unlikely. That's why they size it slightly different. Any comments, any questions? Comments, questions, guys, about the fire pump? Straightforward with the sheets. Derek, don't you think with the sheets straightforward? Nothing, no gimmicks to it? Okay, so moving on. Here's your homework, guys. This is your homework, so please write it down. I don't know what where we number in terms of homework here. Let me see if this were number. Write the number here. Okay. You wish should be at number 13. So can you guys write this is number 13, homework number 13? So what I would like you to do, Karen, is do the same calculation later on for a voltage 208, everything that we did, guys. The only difference is jockey pump 10, 100, fire pump, and the voltage 208. Okay? Now that's, make sure you do that one, 13. Let's go to the next, the next sheet. So everybody, any question about this sheet, guys? The first example of fire pump. The first example of fire pump. Okay, let's take a second example of fire pump. The second example of fire pump, let me show you the sheet that you guys have in front of you. We have, so Derek, the same thing. Look at that. The only difference that we have, can anybody tell me what we did here? We stuck a transformer in between the fire pump system and the power system. We have a transformer. Why would you do that? If your voltage system is 480 and your fire pump is 208, what do you need to do? You need to transform a voltage. So what would you do if you have a transformer? It's a special case. What would you do if you have a transformer? So let me guys walk you through the same thing from the bottom. Look what happened. Start from the bottom. The first 1 and 2 are branch circuit identical. Identical Karen to what we have done. No change. Can you guys see that? Branch circuit 1 and 2, we size them the same. Now, fire pump controller and jockey pump controller identical. We did not change. Can you guys see that? It didn't change from what we've done before. Okay. Now, number 5 is controller feeder size. We horsepower is a control. So okay, controller feeder size, the same thing. Did it change from what we did before, guys? Have you noticed that? Did it change? Same calculation, right? So up to 5, really up to 5, and up to 5 right here. Can you guys see 5? All this stuff, nothing changed. Stays the same. Number 5, or controller feeder size. Now we need a transformer. Now we need a transformer. So number 6, become a transformer. You need, that's new. So this is how we size the transformer. Adam, we take the 1.25 times full load current, divide by the voltage to find the size of a transformer. Then you go up. This is where you can find the actual transformer size, and you go up. Can you guys see that? To size it. Then transformer overcome protection device. Look what happened. This is slightly different. You go the locked rotor current, the transformer, you take the locked rotor current of the two of them. Can you guys see that? Exactly like we did. Then you have to multiply it by the voltage ratio. This is the unique. Can you guys see that? The voltage ratio. After you do what we have just done, Derek, Matt, what we have just done, after you do that, you multiply by the voltage ratio because you're calculating a 208, guys, and you're transferring it to a 480. So you have to take the voltage ratio into consideration. That's new. Did you guys hear me? You multiply by the voltage ratio. Then transformer size the transformer conductor. You take the I primary, find the I primary of the transformer and size it basically. Can you guys see that? Auto transfer switch, same thing from the I primary. Conductor from the main service, the same thing, find the I primary. Conductors from the backup generator, same thing. Overcome protection device from the service side, exactly the same thing, except look what we do. We have to multiply it by the ratio. Can you guys see the ratio, the voltage ratio? Conductor from the backup service, it's basically the 1.25. Can you guys see that? We do by sizing it by 1.25. Okay, shall we go ahead and do that? Any comments, guys? Any questions? So what the only difference is I stuck a transformer right here. Shall we go do the example? Follow these sheets? Yes, no? Everybody's good? Cool? Okay. So that's the only difference. Let's go follow the sheet. Now on the test, Derek, this sheet have to be in front of you. If it's not in front of you, it's really confusing. You know what I mean? It is confusing. So you have to have it in front of you. Follow the sheet step by step. All right, so let's go back to full. Okay, so now I do have a 480 system, the example, 208. It's an F code letter and an E code letter and 7.5 horsepower and 150 horsepower. You guys see what the system that I have? The only difference is I stuck a transformer in between, right in here. There is a transformer in between. We're going to go size these. How many things now? 12 things? Or they still? Yeah, now 13 things. We're going to go size these 13 things. Shall we? Ready? Cool? Okay. So let's go start. So now, the first thing we need to size, Derek, my friend, is find the full load current. And if you guys do that, it's straightforward. That will be 396 amps. We have done that. So you take the 150 horsepower at 208 at table 430.250. That'll get you 396. Straightforward. Then you multiply 1.25 continuous load multiplied by 396. That will get you a healthy 495 amp. 495 amp. Cool? We'll size the conductors. Now, Adam, you take the 495 amps, take it to 310.15p16. There's one little problem. It's a lot of amps. So what do you do if it's more than 400? Derek, ma'am, remind me. Thank you. We parallel. So we're going to go parallel, gentlemen. 495. How many sets? Minimum 2 in this case. So take 2 sets. That will give you 248 amps. Take this one to 2. Take this to 310.50. 310.15b16. This should be 310.15b16. We'll take it correctly. So, table 310.15b16 under 75-degree column. This is a table. If you guys take it there, after you do that, you're going to end up with 2 sets. Oh, the conductors are 3 conductors and 250 KCM and RHW. Done. See how easy that is? Any comments, guys? Any questions? Straightforward, no gimmicks, except with parallel. Bigger conductor with parallel. Okay. Any comments, questions? Karen, good? All right, so let's go find 2. 2 is very easy, 7.5. At 7.5, guys, the full load is 24.2 amps. Same thing, 1.25 times 24.2. That'll get you a healthy 30 amps. And when then you take the 30 amps, that's easy. 30 amps, take it to 310.15b16, and that will get you 3 conductors, number 10, AWG, RHW. If I ask you to size the conduit, would you be able to size the conduit? Yes. No problem. Any comments, guys? Any questions about the branch circuits? Branch circuits, Derek, are straightforward, no gimmicks, nothing. Straightforward. Okay, no change. All right, so let's go to number 3. Number 3 is a fire pump controller. Same thing, guys, we've just done it. You take the 150 to 208 DeWalt 6-4, and that'll get you NEMA number 6. You take the jockey pump to the same table under 208, 7.5 horsepower. That'll get you NEMA number 1. NEMA number 1. Comments, questions, guys? Straightforward, right? That's what it tells you in the sheet. You have the sheet in front of you, and you run it. Run your sheet. Adam, things are good? Okay. Controller feeder, number 5. We're going to go find the controller feeder. The first thing you need to do, guys, is multiply 1.25 continuous load. Add the 2 together, like we've done. 396 plus 24.2. That'll get you 525 amps. A healthy 525 amps. Then you have 525 amps. You're going to parallel them, obviously. 2 divided by 2 to parallel. That will get you 263 amps. Take it to 3 10 to 15 B16 under, this is, believe it or not, B. Under 75-degree column. Gentlemen, you get 2 sets of 3 conductors. Each one of them is number 300 KCM RHW. That's it. Any comments, guys? Any questions? Any comments? Any questions? Does it make sense? So that would be the feeder coming from the, the controller. The feeder coming from the controller. Okay. Comments, guys? We've done that before, right? 5. Straightforward, not a whole lot of gimmick. You pedal them. Every time you hit more than 400 there, mat, you have to pedal. 400 is your cutoff. Okay? Let's go size the transformer. Now, this is new. We need to size the transformer. The way they size the transformer, guys, the same thing. First, you take the 1.25, multiply it by 396 plus 24.2. That'll get you a healthy 500. We just did that, 25 amp. Now you need to size, the transformers are sized mat in kVA. So you have to do the kVA for them. So you take this number, which is basically, you take the 525, multiply it by, what's the voltage system? 208. What's the 1.73? It's 3-phase. Divide everything by 1,000 because kVA is in, these are in 1,000. And when you go there, 189 kVA is the transformer that you need to buy. There's one little problem. 189 does not exist, kVA. They don't exist. So you need to find yourself a standard kVA. Where do you go to find a standard? 7-7, DeWalt 7-7, and that will get you 225 kVA. 225 kVA. That would be the size of your transformer. Matt, Dirk, does it make sense? Karen, Adam, a lot of calculation. If you imagine doing that without the sheet, I mean, it's just, that's why we give you guys a sheet to facilitate the operation. If you want to graduate from Dunwoody, you don't know how to size a transformer, that's a disaster. Ask me for a refund. Okay, number 7. Number 7 is the primary. Number 7, my friends, is we sized the transformer. Okay. Number 7 is the primary overcurrent protection. The primary overcurrent protection. Is that what we call this? Number 7. Yeah. Number 8 is the feeder. Okay. Number 7 is the primary overcurrent protection device. So we're going to do the same thing, guys. Lock rotor current. Remember that lock rotor current business? For the jockey, for the fire pump, it's 4.99. That's the multiplier for it. 150 times 1,000. Divide everything by 1.73 times 208. And that'll get you a healthy 2080 amps, or this one. You go to the jockey pump, apply the same thing for the jockey pump. It's 5.59 from the table that gives you the lock rotor current times 7.5 times 1,000. Divide everything by 1.73 times 208 voltage system, and that will get you. That will get me a what? That will get me a 117 amp. The next step, Derek, is to add them up. Next step is you add them. 208 plus 117, like the calculation will tell you, and you end up with 2197 amps. Okay? Any comments, guys, up to this point? Now remember, this is on the 208 side. if you guys look where the transformer is, here's my transformer. All the calculation that I did is right here, but my overcomputation device is right on the 480 side. Here's my 480, here's my 280. Now I did the calculation on the 280 side, I need to transfer it to the 480. What do? Multiply it by the ratio, the voltage ratio. Because an amp here will be different than an amp here. Will be actually, an amp here will be 208 times divided by 480 times the amp, because it transferred. That's what the transformers do for a living. They transfer it. So the last thing you need to do, gentlemen, is you take, you're going to take that number, let's choose a different color here. So I'm going to take the number that I came up with, which is 2197, multiplied by the voltage ratio. What's the voltage ratio? 208 divided by 480. And that will transfer the amp from this side of a transformer atom to the other side. And if you do that, that will give you 952. 952 amps. Okay, now the last step is to take your 952 amps, take it to 240.6, and that will get you, and go up if it's not a standard, to 1,000 amp. So the primary of that transformer is going to be 1,000 amp. The primary of that transformer is going to be 1,000 amp. Okay, 1,000 amp, straightforward. That's the primary. But do you guys see the issue multiplied by the voltage ratio? Why did we do that? Because all the calculation was done right here. My pump was right in this area. Here's my pump, or pumps. So to transfer them to the other side, you have to multiply it by the voltage ratio. Cool? That's probably the newest version of it. Cool? Questions, guys? Comments? Okay, next, now we need the transformer primary conductor. The transformer primary conductor, that will be number 8. You need to find the conductors. Take your transformer, which is 225K, divided by the primary is 480 times 1.73. And when you do your math, you're going to end up with 271 amp. That's the primary conductor, okay? 271 amp.
Wouldn't you give you when you have to multiply it by 1,000 again and then divide it by 1.73 times the voltage?
Which step are you doing? Which? Number 8?
Yeah.
Number 8? Yeah, you have to multiply the top by 1,000. 225 amp times 1,000 divided by this.
Oh, no, I thought you meant as in like the total KVA, like 225,000 times 1,000 again.
No.
Okay.
No.
Yeah.
No. 225K becomes 225,000 divided by that number. I don't know why I multiplied it by. So we already size it by based on the 1.25. Okay, so then, guys, I want you to help me with that one. So we got 271. So I used to multiply by 1.25, but I don't think there's need anyone. So you take 271 amps. Take this one to, you don't need to multiply. Can you see the sheet? We don't multiply it by anything, by any. We already took the 1.25 into consideration. Can somebody? I need help with the table 3. B10.15, B16, 75 degree Kelvin. Can somebody give me the three conductors? It'll be three conductors. What's the size? 300. The 300? Okay. Any second? 300 kcm RHW. So should we multiply it by 1.25 again? We already multiplied. If you guys look at how we got the transformer, it's already oversized. So judgment, I used to be in the past, I used to multiply by 1.25, but no need for multiplying it by 1.25. Did you say 300? Did we get a second on that?
Yeah.
Second? Okay. I hate because a lot of things are going to depend on it. I hate to carry it. Okay, so that's number 8. The ATS the same way, guys. The ATS right here. My ATS. So I take my conductors. I'm going to take what's my conductor? You take your 271 amp. It's already taken into consideration. Take it to DeWalt 3-12, 3-12. And what's the next standard auto transfer switch, Jelmer? 300 or 400? 400. 400, yeah. So we don't multiply it, 400 still the same, 400 here. Okay, so all right, so that's basically, any question guys about these? We got these. Let's go to conductor from the main. Conductor from the main. This is a main, believe it or not, here. Main. Conductor from the main, same as 8. So do we need to even do any count? So it'll be 3 conductors, number 300 kcm RHW. How about conductors from the generator? Same as the main. Same as number 8. We already calculated. 3 conductors, 300 kcm RHW. 3 conductors, 300 kcm RHW. Now, overconduction device on the service side, same as number 7. So this is number 12, will be same as number 7, and we came up with a 1000 amp. You guys remember the same calculation? Conductors on the generator side is slightly different. The last thing is conductors on the generator side, my friends, which is going to be slightly different. Conductors on the generator side, you need to you take the 271 amp, remember that's from the transformer, then you need to multiply it by 1.25 from the transformer calculation, table 450.3b. Multiply this one by 271 amp, and that will get you 339 amps. And then you take your 339 amps, take your 339 amps, take them to 240.6, and that go up to 350. 350. Any comments, guys? Any questions? Any comments? Any questions? Any comments? Any questions? I'm going to show you the homework that will go with that one. That will be homework number 14, and the last homework that you guys are going to do with your friend Chad. Here's your homework number 14. Now we have a 15 horsepower at 600. The voltage primary is 600. The secondary voltage, guys, is 240. And it's 200 horsepower, and you are to do the same calculation. You guys are to do the same calculation for a friend Chad. Okay. Any comments, guys? Any questions? Does that make sense? Is the sheet understandable, straightforward? Okay. Here's what I'm going to do. I'm going to give you guys 10 minutes, exactly 10 minutes, and I do have one more thing related to actually PTW, related to PTW, adjustable circuit breakers. One example, and that will be the end of our calc for this year. So why don't we have 10 minutes? Let me download my stuff, and then I'm going to go over one more time, like I said, an adjustable circuit breaker. I have a handout for you. Again, one little sheet, and it will help us do the coordination in a second afterwards. So it's related to the PTW anyway. Thank you.